I decided to make one more video for section 4.4 to show some non-Rn vector space examples. So here, let's take a quick look at some non-Rn vector spaces. For example, the vector space M22, the vector space of real matrices with 2 rows and 2 columns. The standard basis for this, we call the standard basis for it, the set of matrices 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Maybe it's clear why this works as a basis. Maybe it's harder to see, but essentially it's just that we can write any matrix as a linear combination of these guys. Like this. And so that certainly shows that this set of matrices spans M22, since we can write any matrix A, B, C, D as this linear combination of those 4 matrices in the set. It's also pretty easy to show that these are linearly independent, and we'll see some stuff like that later on in this example, so I'll save that part of showing that this is a basis for later. So that's for the real matrices of dimension 2 by 2. We call that vector space M22. The vector space of polynomials of degree n, we say the standard basis for this is the set of monomials, x to the n minus 1, all the way down to x squared, x down to 1, right? X to the 0 power. So it's just these descending powers of x from n all the way down to 0 powers. So again, the reason this works is similar to what we did up here for the 2 by 2 matrices. You just write out what any nth degree polynomial would look like. Maybe we say it's an x to the n plus an minus 1 x to the n minus 1, all the way down to a2x squared, a1x plus a0. Right, we could see that any polynomial, if this is a general nth degree polynomial, can be written as just a linear combination of these n to 0 powers of x, n down to 0 powers of x. So that shows that certainly these guys span the space of nth degree polynomials, showing that they're linearly independent. Again, we'll see an example similar to that shows something like that later on in this video. And it turns out the standard basis for Cn, which is n tuples of like ordered pairs, ordered triples, so on, of complex values, is just the same as the standard basis for Rn, namely, for example, for C2, it's just the set 1, 0, 0, 1. Right. It's pretty easy to show again that that easily spans this space of complex ordered pairs. It'd be the same sort of structure for higher n values in Cn. But before we get into big examples, let's do this very briefly. Let's ask, what is the dimension of each of these vector spaces that we kind of define standard bases for? Let's see. Let's start here. What is the dimension of M22? Well, remember the dimension is just the number of vectors in a basis, and here we have a basis of M22 with 4 vectors, 4 matrices in it. So we would say in this case, the dimension is 4. How about the dimension of Pn? Let's see that. The dimension of Pn is going to be how many vectors are in there. And notice we have everything from the nth power to the n minus 1, down to the first, down to the 0th. So if we're actually counting up how many items are in here, there's the 0th one is 1, the first power is 2, the second power is 3. However many powers we're at, we actually have that plus 1. We have the 0th is the first power is the second power is the third, all the way up to the nth power is really the n plus 1 term. So this tells us the dimension of Pn is n plus 1. How about Cn? Well, C2 had 2 of these guys. Just like with the real vector space Rn, we're going to get something similar. We're going to get the dimensions, just whatever n is. Right. Okay, now finally let's get to some of these examples. Let's see some of these in action here. Are the following sets bases for the vector space? Here we're looking first in part A at the sets fg, the sets of functions f, g, and h, where f of x is x squared plus x minus 3, g of x equals, let's see, sorry about that, g of x equals x squared minus x plus 1, h of x equals x squared plus x minus 1. And we're looking to see if this set f, g, and h of polynomials is a basis for P2, the space of second degree polynomials. So to check this, we already know the degree of P2, right, it's just a value of 2 here, would be 2 plus 1 is 3. And we saw earlier that if we already know we have the right number of vectors in to match, if we know we have the right number of vectors in a set to match the dimension of that vector space, we really only have to check that these are either linearly independent or that they span the vector space. We don't have to check both. So for something like this, I just have to check that these 3, since 3 is the number we expect to form a basis, the number of vectors we expect to form a basis of P2, because that's the dimension of P2, all we have to check is the linear independence of these 3. So I'm going to check that. I'm going to write down a linear combination of these 3 and set that equal to the 0 vector, the 0 function. So really what I'm saying is that for any x, for any x, c1 times f of x plus c2 times g of x plus c3 times h of x has to equal 0. All right, this is the equation we're always solving when determining the linear independence. If the only solution to this equation is that all 3 scalars, c1, c2, and c3 are all 0, then we know we have independence, which would make it a basis. Right? 3 independent vectors in a space of dimension 3 would give us a basis. So we're going to just check and see what the solution C1, C2, and C3 really look like here. So let me write this out. F of x is just x squared plus x minus 3. G of x is just x squared minus x plus 1. And h of x is just x squared plus x minus 1. And remember, that has to equal 0 for every x. So this actually gives us a system of equations in C1, C2, and C3. And we set this up just like we have in previous problems. We equate coefficients of like powers of x on both sides of this equation we just wrote, which tells us C1 plus C2 plus C3. The x squared coefficients on the left side of the equation must equal 0, since there are no x squared on the right. Linear coefficients give us C1 minus C2 plus C3 equals 0. And constants give us negative 3C1 plus C2 minus C3 equals 0. So I'm going to pack this up into an augmented matrix. I want to see what those C values can possibly equal. And when I compute this, I get, when I reduce this down using row operations, I actually get this, which implies all three scalars must be 0. Since the only way for a linear combination of f, g, and h to equal the 0 function is if all three scalars are 0, that tells us these are linearly independent functions. F, G, and H are linearly independent. Since we've got 3 linearly independent vectors in this vector space P2, and 3 is the dimension of P2, we saw a theorem earlier that tells us we don't have to check span, we get span for free. We know this forms a basis. For P2. Okay, so remember, whenever we're talking about linear independence, which this problem boils down to, we're always ending up solving a system for those C values. Let's check out this next one, see what it gives us. Same idea, but now we're looking at the set of 2x2 matrices listed here, 0, 0, 0, 1, 0, 1, 2, 0, 0, 1, 2, 3, 0, 1, 2, 3, 4. And we're asking if that forms a basis for M22, the vector space of 2x2 real matrices. Again, we know, since we already saw this above, the dimension of M22 is 4, and we have 4 vectors here. This is the same exact type of problem we saw in part A. We just need to determine, are these linearly independent? If so, since there's the right number of them to make a basis for M22, there's 4 of them, linear independence is all we have to check. So I'm going to jump in and start out the same way. Just write out a linear combination of these vectors. They're really just 2x2 matrices. And say that this equals the 0 vector in M22, which is just the 0 matrix of dimension 2x2. So if I put this all together, all I'm going to do is multiply each of these scalars to every one of their components, the components of the matrix that they're multiplied on. That'll give me, if I do this, and then add them up, I end up with C1 times 0 plus C2 times 1 plus C3 times 2 plus C4 times 1. Sorry, C3 times 1, C4 times 1. All that added up in the first component of the sum that you really get out of the left side of this equation, the previous line. So you get 0 C1 plus 1 C2 plus 1 C3 plus 1 C4. All of that is the first row, first column element of this sum we have on the left. I kind of wrote that one out in expanded form, hoping we could see C1 times 0, C2 times 1, C3 times 1, C4 times 1, all added up in that first component. The others I'm going to go quicker through. Here it looks like I'll get 0 plus 0 plus 3C3 plus 3C4. Up here, it looks like I'm going to end up with 0 plus 2C1, sorry, 2C2. Sorry about that. 0 plus 2c2 plus 2c3 plus 2c4. And finally, bottom right corner, I get c1 plus 0 plus 0 plus 4c4. And all that has to equal the zero matrix, the 2 by 2 zero matrix on the right. Now we just equate corresponding entries on both sides. So we're going to say top left entries give us the equation C2 plus C3 plus C4 equals 0. What's here equals what's here. And likewise, do top right next tells me 2c2 plus 2c3 plus 2c4 equals 0. Bottom left gives me 3c3 plus 3c4 equals 0. Bottom right gives me c1 plus 4c4 equals 0. So again, this is just a system of equations that we have to solve for these scalars. And if I pack that up into an augmented matrix, I get 0, 1, 1, 1, 0, 0, 2, 2, 2, 0, 0, 0, 3, 3, 0, and 1, 0, 0, 4, 0. So let me reduce this down real quick. Let's see what I get when I do this. Bear with me for one moment. Okay, when I reduce this down, I get the following matrix. I get 1, 0, 0, 4, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0. Oops, scratch that. Get a 1 here. Oh my goodness. Get a 1 here. And then a row of zeros. So notice here, we did not end up with a single solution, a unique solution. We actually get multiple solutions of the form. If we just unpack this, anything of the form C1 equals negative 4R, C2 equals 0, C3 equals negative R, and C4 equals R. All right, if we carefully unpack it, that's what we get. And notice there are many solutions, many values of C1, C2, C3, C4 here. There are many possible values other than them all being 0. Plug in R equals anything but 0, in fact, and we get a set of scalars other than all 0 that actually satisfy this equation up here. This means the set of 2 by 2 matrices is not linearly independent. It is, oops, this thing is linearly dependent, which of course keeps it from being a basis. A basis must be full of, must be independent. Okay, so that's the end of this video. I just wanted to make sure you saw some of these non-RN sort of examples worked out, and you get an explanation of what we mean by the standard basis for some of these things. All right, stay tuned for more videos from the next section.